Hi, everybody, and thanks for tuning in. I'm Chris Liedel, and this is my capstone presentation for IBM's Advanced Data Science Specialization that's offered on Coursera. I'll introduce the data set and the use case. We'll go over some data quality assessment, some pre-processing, feature engineering, we'll look at the evaluation metrics, and several machine learning models used in the project. Finally, we'll examine the top two models and the performance of the best model with a skin lesion image from an outside data source. So with that in mind, let's fire it. For this project, I've chosen automated pigmented skin lesion diagnosis from the medical field. The dataset's available from either Kaggle or Harvard Dataverse and contains 10,015 images representative of all the important diagnostic categories of pigmented skin lesions. It also contains a metadata file. More than 50% of the lesions in the dataset were confirmed through histopathology, and the rest through expert consensus or confirmed by in vivo confocal microscopy. The types of lesions are labeled 0 through 6. The metadata file contains some additional information, including age and sex of the patient, location of the lesion, diagnosis type, image ID, and lesion ID. As you know from previous slides, we have a multi-class classification problem with each of the diagnoses assigned to 0 through 6. Since skin cancer is the most common form of human malignancy, early detection is a must if we're to effect simpler and more effective treatments. But access to low-cost medical care can be a challenge in some parts of the world due to remote locations and underdevelopment. Automating skin lesion diagnosis, for instance, with applications on mobile devices can potentially expand access to this care, even to areas where there is sparse or non-existent internet service. To perform the analysis for this project, I chose Python with the standard libraries for data analysis, machine learning, and deep learning. Also, IBM Watson Studio with Jupyter Notebooks. So now on to our analysis. After collecting the data, our first step is initial data quality assessment. High-quality data sets are essential for machine learning, as even relatively small errors in the data can lead to large errors in the system's output. I'll go over a few selected observations in the next slide, but for more detailed understanding of the process, have a look at the notebooks. First, let's look at the target variables and see that there are 7 types of lesions: melanocytic nevi, melanoma, benign keratosis-like lesion, basal cell carcinoma, actinic keratosis, the most prevalent lesion in the data set, as you can see, number 4 there, vascular lesions, and dermatofibroma. We also see we have an imbalanced data set, which isn't unusual, but it's something we're going to have to deal with later in the project. Let's have a look at how some of the variables stack up with one another. First, I inspect the age of the patient and the frequency of lesion diagnosis. The histogram on the left shows us the most lesions are discovered and diagnosed between the ages of 45 and 55, and this discovery tapers off as patients age. The histogram also shows significantly fewer diagnoses below the age of 40. The chart on the right shows us 13% of lesions are diagnosed at age 45, 11.9% at age 50, and 10.1% at age 55 in this data set. Next, I inspect the diagnosis and the location of the lesion. We see that most of the lesions are located on an extremity at 24.2%, lower extremity at 15.7%, and upper extremity being at 8.5%. You can also see that lesions are discovered on patients' backs about 16.6% of the time. These charts show the gender of the patients in association with the number of lesions diagnosed and the location of the lesions. We can clearly see in these charts that men have more lesions in all categories than do women. After the initial data analysis, we need to clean the data and put it in a form suitable for use with our chosen algorithms. This is a list of some of the checks I performed for this project: filling in missing values, correcting data types, encoding categoricals, scaling, performing principal component analysis. Statistical measures are also useful for examining relationships between variables. We can view numeric and categorical distributions to look for outliers and check value ranges. We can also use correlation analysis to give us a general overview of the data set and reveal highly correlated features Highly correlated features are not useful and can cause problems in models, so they ought to be removed. Similar to correlation analysis is mutual information scores. Mutual information scores suggest the importance of relationships between features. The chart on the left is an example of the metadata variables plotted against age. On the right, we see once again the imbalanced distribution of classes. So how will we deal with that? One approach to addressing imbalanced data sets is to oversample a minority class or classes. Most machine learning techniques will ignore the minority class or classes, and many times it's performance on the minority class or classes that's most important. One of the most widely used techniques for dealing with imbalanced data is the synthetic minority oversampling technique, or SMOT for short. SMOT is a type of data augmentation in which new examples are synthesized from existing examples. The chart on the left shows the original dataset distribution, with 66.95% of the lesions being assigned to class 4 and only 1.14% assigned to class 3. The chart on the right shows the results after performing the oversampling technique, balancing out our dataset. Once we've examined and cleaned the dataset, we can decide on model performance metrics and move on to model definition and training. Since we're dealing with a multi-class classification project, we'll use accuracy, the number of true results among total number of classes, along with precision, recall, sensitivity, and specificity. Sensitivity, which is the same as recall, and specificity are used for evaluation in the medical field. Note that we want to see high accuracy, high precision, recall, and sensitivity, and high specificity from our models. The data set is split using 90% of the data for training and 10% of the data for testing. Our model evaluation will be performed using both balanced and imbalanced data sets. Now on to the good stuff. Let's analyze the results of modeling. In order to establish a baseline score, I began with a dummy classifier and a logistic regression model altered for multi-class classification. As you can see, neither of the models performed well on the data and are absolutely useless. Next up was a decision tree classifier that didn't perform any better on the imbalanced data than the multi-class logistic regression model did, but performed very well on the balanced data with 85% accuracy, precision, and recall, and 0.97 for specificity. I chose this as my baseline. Next in line, I chose a random forest classifier, an ensemble of decision trees, and again we see poor results on imbalanced data, but big improvements on the balanced data set with 92% accuracy and precision, 93% recall, and 0.986 specificity. XGBoost, a gradient boosted ensemble of trees and one of the most powerful algorithms, followed, giving 95% accuracy, precision, and recall, and 0.991 specificity on the balanced data set. But I wanted to go further and try neural networks. The first neural network has one hidden layer of 512 neurons, and the second neural network adds an additional layer of 64 neurons and a dropout layer at 0.2. As you can see, both performed equally well on imbalanced data, but the more complex model delivered better results with 98% accuracy, precision, and recall, and 0.996 specificity on balanced data. A grid search over activations and optimizers was performed on the winning model, but no improvement in the results was found. Now let's have a look at our top two models. First up is our runner-up model, XGBoost. XGBoost gave 95% accuracy, precision, and recall, and 0.991 specificity. A more detailed view across classes is seen in the classification report. And we see more detailed breakdown of performance by examining confusion matrix and the probability curves. The ROC curves, the probability curves, illustrate the diagnostic ability of a classifier system. In this case, we use ROC for multi-class classification, 1 versus 1 and 1 versus rest. The higher the area under the curve, the better the model is at predicting the correct class. XGBoost produced good OVO and OVR macro and weighted scores of 0.997. What about our winning model? Our winning model is a fully connected neural network with two hidden layers, ReLU activations for the hidden layers, a dropout layer set at 20% and Atom optimizer, producing 98% accuracy, precision, and recall, and 0.996 specificity. Again, we have a look at the classification report and the confusion matrix for more detailed understanding of how the model is performing. Further, you can see the training and test performance is good, and the model's probability curves are excellent with 1 versus 1 and 1 versus rest area under the curve scores of 0.997, meaning that the model has 0.997% chance of correctly classifying skin lesions. The question remains, will the model really do well on a skin lesion image that aren't included in the data set used to train and test the model? The only way to find out is to feed the model a never before seen image. So let's fire and do that. Here we have it. An image collected by searching a specific diagnosis. In this case, it was actinic keratosis. The image was taken from what appeared to be a reliable source and run through a pre-trained model. If the diagnosis associated with the new image is correct, then our model is predicted correctly. With our accurate model in hand, we can now use it to augment pigmented skin lesion diagnosis. Not only can the model be used to augment in-clinic diagnosis, but by using the model in an application on a mobile device, diagnosis can be made outside the clinical setting, potentially expanding the availability of low-cost medical care. This could be used in remote locations as well, in offline situations where internet service is sparse or even non-existent. Using the model would look something like the following. A digital image is taken of the lesion in question. The image enters the transformation pipeline. The processed image is fed into the pre-trained model. The model makes a diagnosis. This preliminary information could be used by clinicians or remote healthcare workers in determining a course of action. Well, there you have it. I hope you found something interesting to pursue in a project of your own or something that might help you in your own work. If you have any questions or comments, please leave them below. Thanks for watching.